Okay, so I was going to do one more problem on a pendulum, which is also one of the examples in your textbook, but I decided let's do a more interesting one, also later on in your textbook, but it's probably more interesting for me to talk about in a lecture, and you can read the other one, because the pendulum problem basically asks you, for example, if I release it at a certain height with a given length of a pendulum with a certain mass, release it, what's the velocity here? It's basically you equate the kinetic energy with gravitational potential energy. Not that interesting. You can read it. You now have all the tools of it. So might as well me talk about something that will make your other reading easier. In particular, the chapter on universal gravitational potential energy. So let's look at that universal gravitational potential energy. Right? Just to be concise. We have talked about the terrestrial one, right? So the GPE on Earth is mgh. Okay, but this is the one on Earth. I just haven't been saying it. There is the universal one, and it has a formula of minus gmm over r. Okay, so what does that mean? R is the separation of two objects. So if you have two mass, little m, capital M, this system will have a gravitational potential energy. There's an attraction towards each other. So there's energy stored in here, right? There's gravitational attraction towards it. And this is the formula. You can put this in a box as well of the energy that is stored inside this system. Now, a couple of things to point out. Number one, where does that come from? Well, it looks a little bit like the gravitational law, right? It looks like that without an R. Okay, we'll talk about that in a second later on when we find out work done. We'll explain why that is case. At the moment, I'll just give you this formula, much like I just gave you this formula. I haven't explained why it's mgh as well, but we'll do that in the next video. We just want to talk about the ways, how easy it is to apply it once you know it, etc. We'll talk about the origin of these things, of where these formulas come from. And so what is the 2m is these 2m, g is the universal gravitational constant, r is the separation. These are all the standard variables, but you also notice it's negative, okay? The reason is because of this. So I want to see how much gravitational energy is stored over here, right? So if I stretch this out to infinity, let's say if I make r to infinity, what will be the gravitational attraction between the two mass? If I can push this out, I probably can't push it out to infinity, but very, very far. It will be very little, right? So if I make this infinity, if I can actually put these two infinitely far apart, there will be no gravitational attraction between them. So if I set that to infinity, this would be 0. Okay, so understand u when r equals infinity is 0. Okay, now when I bring them closer, if they start having gravitational attraction, should it increase my energy or decrease my energy? It should increase, right? So you should have more gravitational potential energy the closer you are. How can you see that from the force? You can see that from the force as well. The smaller the separation, the larger the force, right? So there should be more energy stored because it's gonna have a bigger effect. So let's see, does this reconcile with it, right? So if r equals to some distance d apart, so I will have minus g m over d like this, right? So if this is d apart, if it's infinite apart, it's 0. Okay, so what's the change? The change in potential energy is final minus initial. The final is d, so it's minus 0. Okay, so I have a negative change over here. So yeah, so equals to a negative, I don't want to actually plug in numbers. So I'll just have, a negative number, okay? So what happens? It looks like my gravitational energy from bringing them from infinity to here has decreased, okay? So shouldn't it increase? But you might think so, but if I decrease it, that's the right number, because that's imagine if I let go, what will happen? These would start to because of the gravitational attraction, they'll start to move closer and closer, and it will start to speed up. So at this point, right, they will have some kinetic energy towards each other. And the loss in gravitational potential energy would now create a gain in kinetic energy. Okay. Maybe I shouldn't put it at infinity since it's a little bit harder to imagine. Let's just make it from D1 to D2. So D2 is when they are closer. Okay, like this. Okay, so what happens if I let go over here? Well, gravity will pull them, the universal gravity would pull them together, right? And if I let go everything at rest, gravity will pull them together, and here they will have some speed like this towards each other. Okay, so what happens? So the change in kinetic energy is definitely positive, right? Because final minus initial, initially there's no kinetic energy. What happens to the change in universal gravitational potential energy? So it's this minus this, right? So hopefully we get a negative, because if one thing gains, the other should lose, right? So we expect to lose gravitational potential energy. So let's see if this is the right sign. So final, so U final minus U initial. The final over here is minus GMM over D2. Initial is minus GMM over D1. Okay. All right. So we have common factors of GMM. Let's pull them out. And then we have positive 1 over D1. And we have negative 1 over D2. Okay. Which one's larger? Well, D1 is a large number, right? D1 is a large number, and D2 is a small number, but this is on the bottom. So if you plug in some number, right? So if I have a large number minus a small number like this, so let's make this 10, right? A large number, so I have 0.1 minus 0.5, this will be negative, right? So this is definitely a loss. So we lost gravitational potential energy and we gain kinetic energy, right? If I do not have a minus sign, so if I had a positive sign over here, then I will have positive D2 and negative D1, right? So I will have positive of a D2 is the smaller number, so I will have positive and negative there. So I will have positive and negative, and I'll get positive, and I'll get the wrong sign, right? So because this will give me a positive number. So you see, this is the sign. That's why we have a negative sign over here. Now, does that mean energy can be negative? Yes, energy can be negative, but it doesn't matter. We already worried about that with the terrestrial version, right? MGH. If I set, it depends on where I set my H. If I set my H at the ceiling, then all the H over here will be a negative number, but that's fine, because it's really the change in U that affects physics, all right? The change can be negative as well, but so it should not worry to you that the energy, the absolute energy itself is negative, okay? What cannot be negative energy, not only, but one of the energy that cannot be negative is kinetic energy, because it's half mv squared. And this is the speed square. This is mass. It's always positive as far as I know. There's no negative mass objects. So there are certain types of energy, heat energy, etc., that has to be positive. But the fact that some can be negative should not bother you. Okay. All right. By the way, this is not why it is negative. It's me just sort of doing a check. If it makes sense, it's negative. And the check says it makes sense. Okay. So let me erase this and keep this formula and see what, okay. So now so in the next lecture, we'll talk about where this formula actually come from, as well as the MGH for the terrestrial version on Earth. But for now, let's just assume we know that fact. This is the universal gravitational potential energy of a system. So this is the gravitational energy stored between two masses, m and m. Okay, it's this value with a negative sign. Okay, how can we use that to benefit our lives? What kind of new things can we learn? Well, for example, let me ask, how fast do I have to throw? Now, if you throw a tennis ball into the sky, it will come back and hit you in the head, right? So if you throw something up, it'll come back. Now, I want to ask, how fast should I launch a tennis ball? Or you know that mass doesn't matter. It'll come back and it'll still be falling at the same rate, right? It's the same gravitational force. So it doesn't matter whether it's tennis ball, marble, whatever. But the question is, how fast should I launch it so it will never come back? So I can actually escape the Earth's gravitational field. In essence, can I calculate the escape velocity? Notice the mass of the object doesn't matter. If you can jump at a certain velocity, how fast must you launch yourself so you can never come back to Earth? All right, that's my question. Let's see if we can calculate it with all we have known. So actually, I think I plugged in the numbers earlier. I think if you can jump at 11 kilometers per second at this speed, this is sort of the critical speed. If you can jump about 11 kilometers per second, you will never come back to Earth. So don't jump that fast unless you want to explore the outer realms of our universe. Okay, so let's see how can we get this number, right? So this is sort of my aim. I'm just looking forward to that. Let's see. So we have the Earth over here. And all right, we have ourselves trying to jump. Okay, so I want to know what is my initial kinetic energy. Initial, and so that I can jump and never return, right? So here I will, do I have any kinetic energy? Yes. And gravitational potential energy? Yes. So I am curious what my V1, this is going to be my A, has to be, okay? So at the far point, I need to find 2 points to compare. So at the far point, this is point 1, point 2, if I have still some gravitational potential energy, right? If U2 is some value, I will ultimately be dragged back, right? I need to be free of any gravitational force. So what I need for this guy is I need this guy to be 0. If I still have any gravity, because look, right? This is the amount of gravitational energy stored between two masses. So if once I'm here, I need to be so far away that there's no more gravitational energy between this, because if there is, it will ultimately drag me back. So I don't want that. Okay. What is my kinetic energy over here? Well, if I jump so fast, right? Here, what is my U? By the way, yeah. So what's my U? My U is minus G. What's the first mass? The mass of the Earth. I'll use this symbol with a cross, and the mass of me, right? This is the mass of me over, what's the distance from the center? Well, it's just the radius of the Earth. Okay, so the distance between my center of mass and the Earth's center of mass is just the radius. Well, yes, the radius and half my height. But that tiny bit is not gonna change my values that much. That's only around two significant figures or whatever. So this is gonna be I don't need to do our Earth plus half of my height. That's fine. Or we'll just use this. Okay. So at the moment, I feel some gravitational attraction with the Earth like this. Okay. And at infinity over here, I don't want to feel any more gravitational attraction. So I want to sort of go out to infinite space that way. What is my kinetic energy there? Well, I don't really care. It has to be larger than 0, right? Larger or equals to 0. I don't care if I sort of stopped. I just don't. So if it's, well, kinetic energy must be larger or equal to 0. If it's larger than 0, it just means I keep going because gravity is no longer pulling me back, right? But I don't care. If I stop there, it's fine. Well, I just want to know when will I never come back. So the minimum, I want to find the minimum value of speed that I need to launch myself, V1 min, in order to achieve that, right? So if you put the equations together, K1 plus U1 equals to K2 plus U2, like this. And if I want to find the minimum K1, then I just need the minimum of these guys, right? So yeah, because everything else, this is fixed, I can't change this. The minimum of this is 0, or actually, in this scenario, I don't want to come back, so this has to be set to 0. There's no choice, and I just want the minimum of this, so that is going to be the minimum value of that is 0 as well. Okay, so what do I have here? Half mv squared. This is little m is my m. Okay, just label that. Plus u1, right? G mass of the Earth plus my mass times my mass divided by the radius of the Earth, and this is minus. Okay, so remember the extra minus sign. Okay, what is my goal? I want to solve for v1. Okay, so let's rearrange everything. So I have half m v1 squared equals to positive g mass of the Earth times my mass divided by this. As you can see, the mass doesn't really matter as long as I jump and launch myself with square root of plus and minus, because of that, 2g m of Earth over r. Okay, the speed, so sorry, when I take square root, that's gone. So the speed will always be positive, so we pick the positive sign. All right, good. Yeah, so pick the positive sign just so that I don't have to write a separate line. And I'll let you plug in the numbers. If you remember, G should be 6.67. I hope I quote these right. You can, with standard SI units, you can double check in your book or just on quick Google. Mass of the Earth, whatever number times 24 kilograms, I think it's around 6. You can double check that as well. And that should be, this one I remember, it's roughly 6,400 kilometers. All right, so change that to meters, so times 10 to the power of 3. Okay, now everything is in standard SI units. Plug this in, and I think you should get around 11.2 times 10 to the power of 3 meters per second. Okay, so that would be 11 kilometers per second. Okay, so see if you can calculate that. Yeah, let me also explain one more thing is how does this tie together with, yeah, I'll leave that for your try to plug in a calculator. Let me explain one more thing is how does this relate to terrestrial gravity? How does this formula relate to the MGH, right? Because MGH should be a special case on Earth. The GP on Earth should be a special case of the universal one. We've done that with weight, right? Equals mg, and we said the universal one is gm m over r Earth square, right? So essentially, this is g, right? So we deduce that g is technically is gm over r Earth plus a certain height from the Earth. So if you drop an apple, right, at a given height, what is the weight? Well, technically the g here is the distance from the center of mass of the Earth to the surface, and then so this plus h squared, right? Remember that should be the correct g to plug in here, but h is going to be so small with respect to this, it's not going to change the number that much. So we are going to say it's roughly this, right? So that's what we concluded before. All right, let's see if we can reproduce MGH from here. Well, yeah, let's. How do we do that? Well, we need to compare the gravitational potential energy between two different heights. Okay, like this, like this. So what's the gravitational potential energy here? The universal one. Well, so on Earth, I'm going to say this is, I'm going to set this height as 0, right? So on Earth, the U, so this is the Earth formula. I'm going to use MGH. So H is 0. So this is 0. And so this is U2. U1 is MGH1. And it's just going to be, right, I'll just call that delta H or just H. Yeah, I'll call it delta H. it's a change in height over here. Okay. If I use the universal formula, then U1 over here is G minus Gm of Earth times the mass of the apple over R of Earth plus delta H, right? So that's the distance from the center of mass of this object to Earth. And then this one, the U2 is minus Gm Earth mass of the apple. Right? All these are mass of the apple, the little m's. I should be consistent, but if I shoehorn that in, it's going to be very messy. So you know what? Let's keep this. I wanted to see that the difference between Earth and apple. And here, when it's down here, it's basically just the radius of the Earth, right? So let's see if the delta U here is the same if I use the Earth formula, and the delta U here if I use the universal formula, if they are the same thing. Okay, so it's now just a matter of subtracting. Let's see. Let's take the larger one, subtract this one, right? So this subtract by this. So on the Earth side, it's easy. It's just mg delta H. Okay, right? It's mgh, and right, that's delta H over there. How about this? So this one subtract this one. I'm gonna use top subtract bottom. So delta U, meaning U1 minus U2, is minus Gm A over R plus H minus Gm Earth mass of apple over this. Now let's pull out common factors. So Gm Earth and apple is common. Now this is positive, right? So I have this minus this. Okay, can I simplify that? Yes, I can. If I multiply this top and bottom by R Earth plus H, and bottom will give me R times R H, and here I can multiply top and bottom by R Earth, like this, right? And now I have a common bottom if I multiply it correctly, right? So I can subtract. So that will give me G M Earth, M apple, and on the bottom R Earth plus H. On the top, you'll see it's this R plus H minus R, right? So it's just H. Okay. I think I call it delta H somewhere, right? So sorry, delta H, just to be consistent. H, delta H. Okay, so delta H, delta H. Okay, and let's put this here, right? So it's equals to Gm Earth M apple over this. So let me put the M apple in front, and I have G of this and G times this divided by R Earth squared plus R Earth times delta H. And I have multiplied by delta H. Okay, so, all right. Now G is roughly this. Can you see it's very close to this? Now, what's delta H? Now, this guy is going to be so much larger, right? 6,400 kilometers squared, right? If you add a height, even if you are a kilometer high, right? So even if you're a kilometer high, you know, that's almost a mile high. You're not going to change this number that much. Okay, so this extra delta H is not really going to change it. So this is roughly just R Earth times R Earth. So this is roughly just MA times G M. Right. So instead of having that, so this really doesn't matter, and really just similar to this. And of course, you see this is roughly, right? This is roughly MA G delta H. That's the change. All right. So you see that this is the change in the gravitational potential energy, if I use the universal formula after 1, 2, 3, 4, 5, 6, 7 steps, I show that it's the same as using the Earth formula. So when you're close to the Earth, how do you know when to use the Earth one and when to use the universal one? Well, if your delta H is small compared to the radius of the Earth. If you are, obviously, if you're looking at the gravitational potential energy between two planets, now that distance, the delta H is going to be it's going to be large compared to this, right? So you cannot use the MGH formula in that case. Okay, so hopefully you see how they're related. Yeah, in the next lecture, so this wraps up sort of the energy approach of looking at motion. And the next chapter we'll look at where some of these formulas come from, and so you get a better understanding of the whole topic as well.